should solve many type of questions, and then they can maybe eliminate a little bit the calculations. But the most important thing is the concentration. So while you are writing, you will concentrate. But as smart students, my advice for all of you, nobody now, just Zainab there, okay? So for all of you, my advice for you, my dear students, is just go and find a direct way to solve the problem. Sometimes you have 3 or 4 ways to solve the problem. Okay, so if you have been given like a Kirchhoff's, okay, network question. So in this case, you can just make the combination of all of these resistance just in one resistance, and then from there you can solve the problem. Maybe you can do that. Sometimes no need actually to go for cross all of these, resistance and find the voltages and then add up, and you just waste your time. Not only waste your time solving the problem very long, but you also may do small mistakes, maybe small mistakes coming from signals, or maybe from the multiplication that you are doing within the calculations. So you need to find best solving method. This is very important because, and this actually it's not coming on the date of exam or on the time that you are solving your final exam or your exam, but actually it is the very long practice, way of learning things. So if you know how to deal with this, by daily basis, by each time you are looking for problems, so from there you can figure out, because actually the material that we have, it is always there, it is always the same. If you are dealing with the electric fields or maybe magnetic fields, sometimes you are required to find the forces coming from the electric charges, or maybe from the forces that are coming from the currents that are moving and then they produce magnetic field. So all of these cases, even Gaussian surfaces, even the amperes, or Amperians loops. So from all of these cases, they have their own special way of treating things together. So sometimes we have integration of something, okay? So that is the 2 laws, like the Gaussian and the Amperians. So how can I deal with that kind of calculation? So I have to know how can I get the results directly from that kind of questions, okay? And also, people, they don't know not only to integrate sometimes, but they feel that it's difficult because they didn't try too much, okay? So solving these kind of problems and then coming back to me, asking questions, sending emails, so that might help us or help the students to know how to solve this kind of questions. So therefore, for each case, each type of material, okay, you need to know how to deal with it in calculations. Sometimes, and it's not sometimes, usually it's the most of the time, there will be no applied question that you just bring the equation and just plug numbers, and then you just plug in numbers and then you get all the result directly. This is not mathematics. So in physics, actually, you need to know the story behind the question before you start to solve the question. So the second one, which is here, 2. And actually this can be related also to the last question, but just here, because the calculations also can be related, to your understanding of the question itself. Why is that? Because you remember last time I gave you a question, and then everybody, or most of you actually, they want to find the force on that wire, But the question was totally different. Yeah, we're giving many information about the wire, about the current flowing in that wire, the length of that wire, but the information mentioned in the question doesn't say that you should go and find force, That information, yes, you can write it down, you will use it, but not for what you are thinking it is going for. So you have to rethink again and read the question many times, then you can find, and you can, let's say, figure out what is question about. So what is question about? So what is exactly questions. The question is about. Okay. So, figuring out what is there, so then you go and solve. Because it's not only a matter of calculations in this case, it's also the matter of solving the question itself. So it's very important actually to just understand the story behind the question. Okay, so again we go back to right-hand rule. This is, as we said before, always, and actually this is my suggestion, okay? Because we have here three perpendicular vectors, okay? So either you use that, okay? Maybe you use this, that, up to you. But my advice for all of you, just use your right hand rule. Sorry, use your right hand, and then make all of these four fingers are the direction of the magnetic field. What about the thumb finger? The thumb here is just the direction of the current, okay? If there is a current. So if there is a current moving, so the thumb will be the direction of that current. But if I have a motion, so I have not only current moving, I have a velocity. So that wire is moving, or that charge is moving. So in this case, also, this is the figure. This finger will be used to determine that direction. Okay. So actually, the thumb finger is just used to anything which is moving. Okay. If the charge is moving, that means the velocity. Or if it's a current, which is also just charges that are moving in all cases. Okay, so let's draw that one here down, that we can see what I'm trying to say here. Okay. So usually this is the direction of magnetic field. We are taking like that one because there are many lines. So don't forget that, many lines. So this is magnetic field. And this is, as I said just now, just the direction of the current, sometimes the charging which is moving, or sometimes the velocity, which is the motion of that wire. So it can take all of these, okay? But usually it's always the motion actually. So it's motion of the currents here, sorry, the motion or the direction of the current, the direction of the charge, okay, if it passes a certain magnetic field. Also the velocity or the motion of the wire sometimes, or even the charge, as we said just now. Okay, but sometimes we're using also for the wire. Okay, so what about the third one? So now we have this one actually is perpendicular to that one. What about the third one? If you can see the palm here, the palm at the center here, we can just make that point here, like that. And that pointing outward direction, okay, it is just the third vector here. And also this third vector is also perpendicular to the magnetic field as well as the current, or maybe the charge, or the speedy wire. Okay, so what is this actually? When we use this, okay? So it depends. Sometimes we don't need that because we have, this is the direction of the magnetic field, and this is the direction of the current is going from right to left. So that will be the direction of the magnetic field, like this. If the current is going that side, so the magnetic field lines will become like this. Okay, so that will be only for two things. No need to have anything in the third direction. But if we are looking, for instance, let's say for a force. Okay, so if we have, let's say, this wire here, and this wire actually it has a current going that side. Okay. So it's going like this. So by using our right hand rule, we know that the magnetic field in this direction will be inside here, okay? So this is B, okay? So let's suppose that we have another wire here. Okay? And this wire also is going up, with the current, going up. So in this case, there will be another force. And this magnetic force will try to make this wire, it has a current, and placed in the magnetic field to move to the left. How I know that it is moving to the left? So I should go to this wire and then also apply the current direction to the top with this thumb finger top. So my hand Okay, fingers, the 4 fingers, it should go inside. Then I can see the palm. The palm is pointing this direction now. So, okay, so this is the force direction in this case. Okay. So now I have this force on this wire, moving this wire to the left here, and we call it the magnetic force. And this is why we have now 3 forces. So this is here will be the direction of that force. Okay. Okay. So that's clear. Even if I have something like, let's say, a moving, let's take an example, another one. So I have a magnetic field is going inside, in this case, okay, like that. So this is a magnetic field. And there is a negative, which is actually usually electron. So electron is just moving, it should be moving, and the velocity now is going that direction inside that field, okay? So it starts to encounter a force, and that force you can see, it's like that. So this is now the finger, as we said, the finger is for I, Q, and V. So here the Q is moving inside with the velocity V, so it's going like that, okay? Okay, good. Fingers inside. So now the force, it should be up, the magnetic force. But because this is a negative sign charge entering that area, so in this case we are looking to the back of the hand, so it will go down in this case. So this will start to encounter a magnetic force like that, and we know it will make like a circle here if we just continue having the magnetic field in all places. Okay? So if we wanted to draw the force here, it would be like that, here, it would be like that, here, it would be like that, pointing to the center of that circle. Okay? So that is another use of the right-hand rule, and this is something you studied before. But if we change the charge of E, instead of having negative 1, if we have it positive, so in this case, if we have a proton here, so proton is going inside, proton means positive charge, so this is negative charge. What will happen to this one actually? It will go here with a velocity V, and then here, let's apply it again. So we have the thumb direction to that side, and then we have the magnetic field inside. But this time the force will be up. Why is up? Because proton is positive, so the effect of the magnetic force in this case would be to that direction, okay? To that direction, and then we can see the path here also again to make it clear for you, okay? But for electrons, it's actually moving to this direction. Okay, so this is just a small application of using right-hand rule, okay, in the magnetic fields for forces, okay, whatever, just a very simplified way of doing that. But the problem during the exams, okay, students, they are not aware about the induced direction of the magnetic field, because to use this rule, hand rule, you need to understand what is actually the magnetic field that you are looking for, okay? And what is the direction of the current, and also forces. Sometimes you need that to have also the velocity. So you need to know actually what is the magnetic field that you are looking for. Why I'm saying this, okay? Because sometimes the magnetic field can be produced, as I said, from a wire. So you have a wire and then you can produce magnetic field. But, and this is also another question that I gave in the last exam, sometimes you have already there a magnetic field which is going down, okay? So if you have an original magnetic field, so this magnetic field is not coming from the wire, okay? So there are 2 actually magnetic fields. One is origin, or it's placed there from the beginning. We didn't do anything with that. But there is another one which is just, okay, induced by the current here. So, and that also will be like going inside. So it will be another one going inside in that area. And this is actually, if this is I1, so this will be B1. Let's call this one B2. So in this case, in this area, actually, you have what? You have now 2 different directed magnetic fields. So you have to know which one you will take. Why is that? Because somebody come here again and then placed another wire, let's say. So I should know what is the direction of that magnetic field in this case. How I know that? How can I understand? Let's take this one out, and then from here I can just expand my space to explain the things for you. Okay. We know that we can calculate this directly from the Pythagoras theorem. So we know that P total, we have two perpendicular magnetic fields, so then we can take it like that. Let's say Py squared plus Px squared. Okay. This is easy for you to calculate. But actually the most important thing is the theta between them. So if I have two perpendicular things, let's say that this is going this direction and this one going up. Okay? So you will move that one here, and then you get the resultant vector like that. So we need to know what is theta here. Okay? The theta here, which is the angle between the resultant vector, which is in this case pt, okay, far away from the x-axis in this instance, but also we can take the other one. It's up to you actually. It's, I mean, the way of you drawing things. But please don't find theta for me and you didn't draw it like that. So I don't know which theta you are speaking about. I should know which theta that you are telling me. And actually this is not happening also in the magnetic field, adding also in the forces, in the electric forces, as well as in the magnetic forces. Okay, afterward, after you determine the direction, now for instance, let's say that I know this is the direction of BT. Okay, and let's say this is the direction of the wire. Oh, so now the angle is not 90 in this case. So it's not always 90 as we said before. So you remember that relation between the force equals ILB. What here? ILB? Zainab? Yeah, excellent. Sine theta. Why we add sine theta here? Because we have been told before that it's not always perpendicular. Sometimes they are in parallel. So if this one actually, they are parallel together like that, the eye is moving like that, so there is no angle between them. So in this case, we can say that the angle here is 0, so sine 0 is 0. Okay? But now we have an angle between them. Okay? So it depends actually if the angle is this one, in this case, or maybe that one. You can use also this other one. There is a current is moving this direction, for instance. Okay? So you have to look for theta here. Okay? And use that theta in your result. It's not always perpendicular. Okay? So for people who are finding the PT in this case, for instance, in this case, okay, they should also find tan theta, which is just equals to the magnetic field in the y direction. We are not saying only in y and x, but they are, I mean, they are perpendicular, so it should be between x and y, it should be between x, z and x, maybe z and y. So it depends actually on what you are looking for. Okay, and then from here you can get shift, as you know, to get the, tan inverse, okay, of this one, by over, yes, px. Okay, from here you can get the theta. So this is the way to find theta from the calculation. So from the Pythagorean theorem. Okay, so generally now we just highlighted certain issues in physics 2 course generally, and as you can see I just focused on skills, because skills they can introduce to you, like the right hand rule, they can bring to you the right formula, okay, and also they can find for you and help you to find the angles that you need, and then you can make your own calculations very correctly. So understand the skill and the story behind the question, and then you can solve the questions easily. Okay? You do this practice when you ever have a question in your, in your practice. I mean, it's the book question, textbook questions, or maybe any kind of question related to our topics. Okay? Okay. So this is in general. I'm trying to say this, but there is something else we can also add regarding the understanding the question itself. Okay. So before you start to solve, relax, read the question. Okay, read the question very slowly. Okay, try to understand first your first impression about the question. So ask yourself firstly what the question is looking after. Okay, so are they looking after the magnetic field? Okay, they want to have, or they want you to figure out what is the let's say electric current. Okay, so which electric current in which cases. Okay, so you just understand what they are asking you to find or to get. Okay, so from there, understanding the question is the most important step. Then you plan how to solve your answer. How can I plan to solve my answer? First of all, what is the best, direct, easy method that can I use to achieve the answer directly? No need to go through all of these kind of let's say trying, because people, what are doing, or students, they try and they do mistakes, and then they come back again and they try and do mistakes. But if you try first of all in your mind, thinking again and again, if I do and start with that, I will reach this. Okay, so by this I can't find that because I need theta. Theta is not mentioned there. Okay, so I go back again. If I just think with your mind before you write anything, but you can write. I mean, if it's up to you. I mean, but at the beginning you make your plan to solve the question. Okay, and sometimes if it's too hard for you to solve the question, just leave it. Leave the question. Okay? You don't spend a lot of time, especially at the beginning. So start to move to the second question. Maybe you can solve it easily. Then you move and just cover all the other questions. But if you if you just finished, okay, the easy questions, then you start and program your time for the questions that needs more time, little bit, and you make your strategy. Sometimes now I give you a little bit. I mean, like, ideas that can be used. Okay, so I give you an ideas that can be used to solve certain type of questions. Okay, so let's start with let's say proof questions. Okay, proofs questions. So in proof questions, or drive this kind of equation, or this kind of equation, it should be equal to that. How can I prove that? First of all, I will look to the relations. Okay, so if there is a relation between V and I, okay, I expect people that are talking about ohms, so maybe R, or maybe they're speaking about B. Okay, or maybe they're speaking about E, which equals to E squared into R, or maybe they are looking for, different kind that can relate I maybe to B and B to F. Many things there. Okay, there are many things. So if there is a relation is stated here inside, so either I can start, okay, from components to the full form, or the opposite. I start from the full form, okay, and then I make it small fragments, and then try coming and bring them back to the form again. Okay, so let's make this one bigger, like that. So what I'm trying to say here, you have two approaches actually, so 1 and 2, or A and B. So either you start looking for the problem itself, and I need to, what is the question, okay? Please prove that this relation is like that, or find this, okay? Or show us how can we reach this, okay? To reach this, you know that there are many variables here, okay? And these variables, they are coming maybe from 3 or 4 equations, okay? So you start to work actually backwards in this case. So how can I start from small things that if they are added up in a very fashion way, they will produce this relation, okay? This is one way of thinking. But if you didn't succeed in that, you should look with the opposite way. So this is like integration, and this is like differentiation, okay? like, like this, okay? So it's like integration. So I integrate and add sum, okay, summation, all of these small parts to find the final question. Or maybe I can start with the big one, which is already given, okay? Start to defrag, to make it small, in small fragments, okay? And I can look for these small fragments. What are the relations between these fragments? How can I just make a relation between these two and these two together? From here, I can go and build again the same derived relation. So let's start from one, just make it like, this is like, also in physics we can say, this is like what, Shabab? This is like fusion, you know fusion? Okay, and this is like fission. Fission, هذا نسميه الاندماج، اوكي، هذا نسميه الانشطار، اوكي، مثل القنبله المنشطره والقنبله المتجمعه يعني. Okay, so you can fuse a certain kind of, components of that derived equation and then fuse it and make it in one place, okay? Or maybe you can just, start making the large one into small, small components that can be related, but here you have to be, smart. How can you relate these together? And then you figure out how can you add them to reach again or back again, here or here. It's at the same time, same thing actually. Okay. Okay. So this is just some ways of understanding how can we, treat such kind of proof questions. Okay. Let's now move to another techniques that might help us in solving the problems. Okay. Sometimes we have, let's say, curves. Okay. Curves. So in curves, or let's say it is just x and y relation like that. So if you have any relation between two variables, they are moving and they're making they are changing, and they're making the relation between them in terms of plotted graph, okay? So if they are plotted there, they will see the curve. So this is actually indicating the line or the curve that explains the relation between the variables x and y. This kind of questions, okay, they should always grab to attention that there is a relation between the variable here and here. So let's say that this is I and this is V, okay? What is the relation between this and that? I can predict that actually from the curve. So if the curve it has a linear, let's say, proportional relation between this I and V, so in this case I can say, as we increase the voltage, the current will increase. Okay, and this is actually the Ohm's law. This is something we know. Okay. But there is something else. We know that there is a slope here. Okay. And the slope is just delta y or delta x, as you know from math. In this case, delta y is just delta I over delta v. Oh, but we know from physics that R, okay, we know R, which is the resistance, equals to V, delta V over delta I. So in this case, is slope now in this case is just 1 over R. Okay? So we need to read the figure. We need to read these curves or these lines, okay, or these relations from the slope itself. First of all, this is a constant slope, okay, because we have a straight line. This is from math. That's something you know from before. But from physics, we know that this slope, 1 over slope is just the resistance in this case. Why is that? Because we put I at the y coordinate, and we put also v at the x coordinate in this case. What about this in this case? Let's compare this one with this one. Okay. So let's take that, and then we put this one here. like this. Okay, this is again the slope. But what is here? Let's call this one V, and here we have I. Oh, now we have the slope equals to delta y again over delta x. Actually, this is delta y. So this is delta y, okay? And this is, yes, excellent, delta x. So we know delta x now is I, delta I. So this would be delta I down there. And we have here delta v, yes, excellent. And this is, as we know, delta v over delta I, just r. So this is, in this case, r. Oh, so now we have the constant slope of this straight line is just the resistance directly. So if I have been given this figure, I can figure out easily, okay, or calculate r as a slope, okay. Now, understanding these basics, very simple basics, you can just do more things here. So let's say that we have slope 1 like that, or maybe slope 1 like, slope 2 like this. And also we can make also another slope here. So this is 1, and this is 2. So now, if I asked, okay, what is the max, or compare the resistance that coming from experiment number 2 to resistance coming from the measurements that made by the experiment number 1. So then we can say that straight line number 2, it has, yes, has larger slope. How I know the larger slope? Because actually we know that this is the theta of this one from the x-axis, and this is the theta, large theta for the, this is theta, this is alpha, okay? So alpha is bigger than theta in this case, so we can say that it has a larger slope, and we can also measure the slope by knowing the delta y over delta x, okay? So we can get also the difference between these two. So in this case, we can say that R2 from here is larger than R1 directly. Why is that? Because we know they are different in slope, in two slopes. Easy. What about here? Oh, as we said that there is an inverse relation between the slope and R. So in this case, we can say that R1 is larger than R2. Okay? So this is the difference between these two slopes and curves, and the physical or the physics that we can get from. Okay, this is actually very easy. Okay? Usually, this is the basics. But from here, understanding the slopes, understanding the y-axis and v-axis coordinates that can play a role. Okay, this also remind me of something else here. Now I can talk about directly, which is the loop. Okay, formation. Okay, so let's say that this is a solenoid. Okay, and this is also another solenoid. Okay, so this is solenoid number 1, solenoid number 2. Now, I want to find what is the magnetic field inside if there is a current is moving from here, and what is the magnetic field inside if the current is moving from there. Okay? So everybody at the beginning, he will say, oh, that's easy. We know if the current is moving from here, okay? So the current flow like that. So if the current is going, let's say down, so it will go that side. Okay? So we can just hold any wire of this. So let's say we're holding this wire, then like that, like that, like that. Okay? So the magnetic field will be from here to there, and we know that this will be S and this will be N. Oh, stop, please stop. This is totally wrong, Zainab. What is the solution here? We should look for the outside wire that we can see. Okay, so we have like two different kind of turns. You see, here when we turn like that, so that part goes down and this goes up. So this is actually what we see from outside. So this is actually the part of the wire that is actually pointing to us. This is also part of the wire that's pointing to us. So this is part of the wire that's pointing to us, okay? You can see these points here. It's on the wires that is outside, it's pointing to us. What about this? These are actually the back wires. They are actually at the back of the cylinder, because this is like a cylinder, shape. What about here? You can see. If you come here and then see, you can see that this is the front wires again. Oh, and these actually, as you can see, the wire here going like that, and then coming from backward like this, and then front like this. Backward, front like this. Oh, so that is the direction of the wire. Here, what about here? It's going like this, and then moves like that, like that, like that. Oh, now it's clear. Okay, so what is the first thing that we should do here? Okay, you just draw the direction of the current through all of these tubes. Okay, when you draw that, it will be easy for you. Now you use your right hand rule, and then make your thumb finger to the direction of current here. Okay, so you take this loop only, so the direction is going like that, and you are just like holding the wire, so it's like going like that, so the magnetic field will go inside. Here also, like that. Here also the current is going down, magnetic field is from here to here, like this. So overall, the magnetic field will move like that. So the second thing, you should draw what? The magnetic field line's direction. Okay? And we said something here that inside a magnetic or a magnet, so we have it from S to north. Why it's from S to north? Because outside